Один экран. Задержка. Вот эти штучки. Вот.
Это общий 2.
Да, и может быть увеличить как-то. После вот так чего. Так, вот часть. Все. Ага.
Ну, просто быстрее.
Я понял. Хорошо. Спасибо. Okay, so today we want to do two papers. One is going to be Aumann, 1987, and another one is going to be Genskov and Kamenitsa, 2010 or 2011. But okay, so we start with Aumann. So here is an example. Suppose we have a two-player game. We have player 1, player 2. Yes, so I will just add this to the course list. Okay, and payoffs are as follows. So this is B1, B2. This is A1, A2. Zero, 3, 3, 0, minus 1, minus 1. Okay, so let's find all the Nash equilibria in this game. And let's find, okay, so what the payoffs they give. Okay, so can you tell me what the pure straight equilibria are?
B2 dominates B1?
Is it?
Or no?
No, sure. Like nothing dominates.
A1, B1 is a pure straight.
A1, B1 is a pure straight equilibrium, right? Because if this is played, player 1 doesn't want to go down, player 2 doesn't want to go right.
Mm-hmm.
And similarly, this.
B2, B2.
Yeah, because it's a symmetric game. Okay, so that would be pure straight equilibria, so I'll just draw the payoffs. This is a payoff of player 1, this is player of player 2, and now we have, okay, so A1, B1 is 0, 3, so it's here, so 0, 3, this one is 3, 0. Okay, now other outcomes are minus 1, it's somewhere here. It's not a Nash equilibrium. And then a good outcome is 2 and 2, which is not a Nash equilibrium either. So here we have Nash equilibrium, here we have Nash equilibrium. Okay, so in these outcomes, players get just 3 units of utility. Here they get 4 units of utility, which may be like more efficient. For example, it's more efficient than to have 50% that and 50% that. So what about mixed strategy equilibrium? Can you find the mixed strategy equilibrium? So how would you do that? So what's the first thing we do when we compute mixed storage equilibrium? Okay, we need to assume something is mixed. Say it's mixed with probability alpha and 1 minus alpha, these two storages. So what should be alpha for player 1 willing to mix? So it's alpha 1 minus alpha, beta 1 minus beta. Yes.
Alpha b1 plus 1 minus alpha b2 should be equal.
Alpha, what do you mean alpha b1?
No, I mean
What's
b1.
what?
So
How
we
to?
we can compute the payoff of the, let's say, second player.
Okay.
It's going to be alpha times 3 beta minus 1 minus beta.
So if
Plus
he
1
gives-
minus alpha on there.
So if he goes strategy b1 or what?
So no, can we just calculate the payoff of the second player?
The second player, sure.
And it's going to be alpha. So if he plays b1, he plays b1
Yes.
alpha times, and his payoff if he plays b1 is 3 beta minus 1 minus beta.
Okay. And so this is what player 2 would get if he were to choose b1.
Yes, so he chooses that alpha times, let's
Mhm.
say. So we multiply alpha by that thing,
Okay.
and add 1 minus alpha and multiply by 2 beta plus 0.
Okay. And so what?
So that's the payoff of the second player.
Yeah, in a profile of mixed strategies in which we mix beta 1 minus beta, alpha 1 minus alpha. So how does it help you? So this is what player 2 would get, right? And in equilibrium we assume that player 2 knows the strategy of player 1. So he knows beta. And he chooses alpha. So beta is his belief about player 1, alpha is his choice.
So we just maximize it by
Yes.
alpha.
Yeah, so we need to maximize it by alpha. And alpha must be staying between 0 and 1. Okay, so now what kind of function is that?
Linear or normal?
Linear in alpha. So we have a linear function in alpha, and we need to choose alpha between 0 and 1. We want to maximize linear function, and need to choose between
it gonna be 0 or 1?
Generically, yes. It will be 0 or 1. And in that case, what does it mean it's 0? It means that player 2 would strictly want to play b2. If it's 1, player 2 would strictly want to play b1. But it would not be good for us, because what we'll do is just the player will play a pure strategy in equilibrium, to which, in this particular game, the second player would best reply with a pure strategy, and we are back to pure strategy equilibrium. Now, we want to have mixed strategy. So how can it be if we have a mixed strategy?
Should the payoff of the second player be equal to the payoff of the first player?
Well, in general, they're not comparable. They're one is expressed in terms of utility of player 1, and another in terms of utility of player 2. And this is just, these utilities, in general, they're just a representation of their preferences back to 2 weeks ago. Okay, so now, so what does it mean I have mixed strategy equilibrium? It means that player 2 chooses some alpha strictly between 0 and 1. So he chooses some alpha somewhere here. How can it be? So you maximize the linear function by choosing alpha. And it is optimal for you to choose alpha strictly between 0 and 1, not the endpoint. Is it possible to have this thing?
It seems like not, because alpha should be infinitely close to 0 or 1.
So for every function like that you're saying, I cannot choose alpha being 1/2 and it would be optimal.
No, because there would be another alpha, which is in which the payoff would be more. If we do it like this.
What if this function is a constant? Like,
This function shouldn't depend on alpha.
yeah. So if this function is a constant, okay, so if the graph of this function is just, it's not like that or not like that, right? Because if it's like that, we choose alpha equal 1. If it's like that, we choose alpha equal 0. The only intermediate case is just precisely when it is flat. And in that case, player 2 indeed will be willing to choose some intermediate alpha. Okay, so now what does it mean this is constant? That means that this expression, x, must be equal to this expression y. So as I put more weight on x or more weight on y, I should be indifferent. Okay, the condition, therefore, x equals y. Yeah. Okay, so this gives me a condition for when player 2 will be willing to maximize. What's this condition? This condition is just condition on choosing b1, his payoff has to be the same as condition on choosing b2. Okay, so this is condition on choosing b1, this is what it gets. This is condition on choosing b2.
That will give you a value of B2.
Yeah.
Of B.
beta.
Of B.
Yep. Yeah, this gives me a value of beta. So this is a general thing, from indifference condition for player 2, I obtain the probabilities with which player 1 should be mixed in equilibrium. Okay, so this gives me a condition. And similarly, I could write down condition for alpha. What should be alpha in equilibrium? In equilibrium, alpha should be such that player 1 should be indifferent between choosing alpha A1 and choosing A2. Okay? And this is a general way how to find mixed direction Nash equilibrium. Okay, so now in this particular example, what do we get? We get that 3 beta minus 1 minus beta has to be equal to beta. Okay, and this is the same as beta equals to 1. So to beta 1/2 1/2.
Beta equals 1/2.
Okay. 3 beta minus 1 beta, 2 beta. Yes. Yeah. So should be 1/2 1/2 for this one, right? So it's 1/2 and 1/2. Then for player 1, the game is symmetric. It should be also that the second player mixes 1/2 1/2. It's just because the game is symmetric. Okay, so then we have this third equilibrium. So we have two Nash equilibria. What's the payoff in this Nash equilibrium? How do we compute it quickly? So one way to do it is just how we told is we write this thing down. But we know that it doesn't matter because it's a constant for player 2. We could just pick any. Okay, so 50-50. So each of these outcomes obtains the probability 1/4. Okay, so if I'm player 2, I get with probability 50%. So it's just the value I get is 1. And the second player, because the game is symmetric, he gets 1. So we get 1/1. Then we get Nash equilibrium 0-3. And then we get 3-0. Okay? So we have 3 such Nash equilibria in this game. So now, so the original game, we have outcomes -1, -1, 0, 3, 2, 2, and 3, 0. This 2, 2 should be somewhere here. It's 2, 2. It's above. That's okay, something like that. Okay, so now, if I draw you this polygon, inside of this polygon is just all the expected payoffs I can get by randomizing, right? So for example, say I do a random number generator, it picks me a cell and says the player should play this cell. Okay, so this is what I get. So now, of course, if I just simply tell my players, look, this is what you should play, for example, you should play this cell. This would not be good, they would not follow. Because if, for example, player 1 thinks that the second player is playing B2, he will deviate and play to this cell. Alright? So I cannot get, in general, everything inside of this black polygon. Even though, like, if I ignored players' incentives, what they want, I would be able to do it. Okay, so now the question is, okay, so if I care about players' incentives, what can I get? Or what could they get? What could they implement? What types of payoffs they can obtain? So one way for me to implement something is just to tell them that they should play a Nash equilibrium, right? And if I tell them the Nash equilibrium, maybe if they both believe that the other person will follow, they themselves would find it optimal to follow. So it would be like a self-fulfilling recommendation. Okay, by doing so, I can get these 3 expected payoffs, 3 points. So now, can I do more? Like if I'm a person who tries to like organize the play of this game, understanding that these players always want to maximize their payoffs. So can I get, for example, payoff free like this 1.5, 1.5? Can I implement such a payoff on average? So, for example, suppose you're player 1, you're player 2, right? And I come to you and I want to persuade you to play the game in such a way that you will get on average this point.
In that case, we agree that at least one of the players has incentive to deviate, right?
To deviate, no, but okay, so I didn't tell you how. Okay, so one of the recommendations for me is to play a cell, right? There is no cell which has free halves and free halves. 1.5, 1.5. Right? So there is no such stuff. But maybe I can use a randomized recommendation. For example, maybe like I can do the following thing. So I flip a coin first. And it's a fair coin. And I tell you, look, I look at the coin and I see that it's heads, you should play this pure strategy in equilibrium. And if it tails, you should play this one. Okay, so conditional on seeing the coin and seeing my recommendation, you will be told which equilibrium to play. Okay, and maybe you will follow this. And will play the Nash equilibrium. But now, because I flip the coin 50-50, right, so each of you will get the combination between these two Nash equilibria, the midpoint of them. So now, if I start randomizing differently, I can generate any convex combination of Nash equilibrium pairs. And I could like implement it. I could make you to play in such a way that you, if you're rational, you will be willing to play and follow my recommendations, and in the end will get the expected payoff which corresponds to this convex combination. Okay, so by doing so, I can persuade you maybe to play any point in this blue triangle. Okay, this is not a, this is something, but this is not very much because, well, for example, there are some points which are more efficient, in which you get more. Okay, so the question is, if by, okay, so for example, randomizing among Nash equilibria, I can get this thing, is there a way for me to organize a play in such a way that you would want to play something which has a higher payoffs? Is there a way for me to make it better for you to play this game? So I'm allowed to randomize, I'm allowed to tell messages. Maybe, so one of the things, right, I could try to exploit. I could try to separate you in different rooms and talk with each of you individually. Maybe, for example, I could give you one recommendation, part of recommendation, another of you another part of recommendation, depending on the outcome of my randomization. You, of course, in equilibrium, you would have to understand that, okay, so I might try to tweak this recommendation, so you understand that you get some recommendations for some probability, you get another recommendations for another probability. So what's problematic about Nash equilibrium in this game? So the pure strategy Nash equilibrium, right, they get sum of payoffs which is not the best, which is less than 4 or less than 3. Now, in pure strategy Nash equilibrium, this thing happens with probability 0. if we go to a mixture, the problem is that we start playing this one with probability 1/4, but it gets mixed with a very bad outcome, which is also played with probability 1/4. Okay, so we don't want to mix in the bad outcomes.
So we can just persuade players to never play -1 somehow.
Somehow. Okay, so if I just talk to you publicly and you hear all of my recommendations, then maybe okay, so you get the same information and maybe there is no extra way for me to tell you what to play. But suppose I'm able to separate you in different groups. I send you emails. Okay, I send email to you. I say, why don't you play today strategy A1? And I send email to you and say, why don't you play strategy B2? Maybe in another outcome of my random number generator, I say, why don't you play strategy B1 and you play strategy A1? Maybe it's some other. But the thing is, like, I'm going to be sending you private recommendations. What you would understand then is just you understand the probabilities, the overall probabilities when I send this recommendation, that recommendation, that and that. Okay, you understand the whole probability distribution over these 4 cells, and you learn only your own recommendation.
So you learn on recommendations that give you, and also on the outcomes of the games, right?
So you don't learn so you know the game, so it's common knowledge between you. It's common knowledge that I'll be sending this with probability P1, this with probability P2, this with probability P3, and this with probability P4, which is just 1 minus the rest.
Maybe we would be willing to play A1 and B2 if we know that B2 is big enough or something like that. That we both are going to receive the recommendation to play that set of strategies that give us 2 and 2 as payoffs.
Mm-hmm. So maybe I think you go in the right direction, but so it's basically okay. So the setup is the following. I tell you the following. Look, I'm gonna flip a coin, like a very complicated coin, which gives me probabilities P1, P2, P3, and P4. Okay, I observe the outcome of this random draw. I don't tell you what it is. I will tell you partial information about it. To you, I will send you whether it's this or that part of outcome.
So whether it's
To you, I will send you if it's this or that.
So A1 or A2 and B2, B1 or B2.
Yeah. So I'll tell you okay. So for example, this will tell me I need to send recommendation A1, B1. Okay. To you, I send your part of recommendation and say I tell A1. To you, I send your part. It's B1. Okay. So if the outcome is this one, I say okay. So you, I would send email which says A2. To you, I would send still the email which says B1. Okay, so now, so suppose you understand these probabilities and I follow them. So what happens then if you receive a message? For example, if you receive a message A2. You don't know what he's going to play.
But we know the P1.
Yeah, you know P1, P2, P3, P4, you know the example probabilities. And now suddenly, for example, you're sitting in your office and you obtain an email from me and I say to you A2. Okay, so what's your Bayesian inference about it?
Well, you should update your probabilities.
Update your probabilities. You know this is not that part of the table, right? This is what's left. So you still don't know what the opponent will play, right? You don't know what he will play. You don't know if he will play B1 or B2. But you can form conditional probability assessment of that. Because your conditional probability, what we want, he will play this with probability P3 divided by P3 plus P4, and this one is going to be P4 divided by P3 plus P4. Okay, so this would be the belief of player 1 if he receives message A2. Okay, so now, so what is the extra condition on all these constructions that it all works? So we know what, okay, so for example, let's say this is going to be P1, P2, P3, P4, and I send to my players their messages. So for example, say I send to the player message A2, recommendation A2 and conditional on my message A2. This is the probability beliefs.
So the player 1 should think that the player 2 will play B1.
No, but he wouldn't play. He wouldn't think that player 2 will play B1. He will play with some probability. With this probability, player 2 will play B1. With this probability, he will play B2. This is the belief. But now, in order for my construction to work, it must be that when player 1 hears this recommendation and forms such belief, player 1 should be willing to follow the recommendation. Right? A2 indeed should be optimal against such a belief.
But we want the player 1 to play A1.
A2, I send the recommendation. Say the recommendation for player 1 is A2.
No, okay, but we want to do.
We want
We
to
get
to get this one with high probabilities. We want to get this one with low probabilities. Yes,
But-
eventually.
okay.
I'm just so far I'm considering the general case, and then we will ask a question of how do we get this one frequently.
Okay.
But now, suppose I'm in the position. Okay, so I say will have this recommendation will happen with probability P1. Say 20%. This will happen with probability 50%. This will happen with probability 20%, and this will happen with probability I don't know what's left 10%. Okay, so some probabilities, say it's 10%, 50%, 20%, and then this one is also 20%. Okay, so what does it mean? It means that when I send the recommendations, you guys just receive these messages. For example, if I flip a coin and it tells me this cell, I send to the first player this recommendation, and to the second player I send that recommendation. Now the first player doesn't know the recommendation B1 or B2 I sent. Okay, so conditional on that, she does Bayesian updating, player 1. It's 20% and 20%, so it's after Bayesian updating, it becomes 50 and 50. Okay, and now first player says, okay, so I think my opponent plays 50-50. Am I willing to choose A2? Well, for 50-50, we already know that he's indifferent. So, in particular, he would be willing to follow the advice. Here, for example, suppose we have this recommendation to play A1. So what happens? Suppose I'm player 1 and I hear a recommendation to play A1. What's my belief about the second player? How he plays with this distribution, like 10, 50, 20, 20.
1/6 and 5/6.
Mm-hmm. Yeah, okay, so I think it's 1/6 B1 and 5/6 B2. Okay, so now I think it's very likely he plays B2 and very unlikely he plays A1.
So I should play A2.
So if I play A1, I get 2 times 5, 6, so I get 10/6. If I get A2, I get 3 times 5, 6, so 15, 6, 15 over 6, minus 1 over 6, so it's 14 over 6. So for me, actually, it's, the best reply is to play A2. Right? So if I hear recommendation A1, I update and I conclude that it's better to play A2. And for such probabilities, my idea wouldn't work, right? Because I'll send you recommendation A1, you compute, and you says, look, I don't want to follow your recommendation. Okay, so that's not a good set of recommendations.
Okay, so we get a system of inequalities.
Yes, so basically we're looking for some construction in which I assign probabilities P1, P2, P3, P4, and I require that for each recommendation player 1 or player 2 receives, she or he indeed wants to follow that recommendation. So that's my whole system of restrictions. So whenever this system of recommendations satisfy all of this restriction, this system of recommendation is called correlated equilibrium. Okay, so this is called correlated equilibrium. This is was devised by Aumann in '74. So, correlated equilibrium is just a measure on outcomes of the game, such that it's basically like on outcomes of the game, meaning recommendations of to player 1 and to player 2, and if we are in more than 2 player games, to each player. Such that after hearing his recommendation, a player who makes a Bayesian updating does want to follow this recommendation. So now, suppose I'm interested in correlated equilibrium in this game. Of course, with correlated equilibrium, I can do any Nash equilibrium. No problem. But can I do anything better? Can I go outside of the blue triangle? So for example, suppose I want to give my players
Well, you should write the system of inequations, solve it, and then see what probabilities do you get. I think it should be more than blue triangle.
Yeah, so that's true in general. You need to write down the system of equations, solve it, and it's actually relatively simple system of equations because it only has 4 unknowns, so it's quite computable. It's easier to compute in general than to compute a Nash equilibrium. So for this particular example, let's not go and solve for all the correlated equilibria, how they look like and so on. But let's find at least one correlated equilibrium which gives 2 players a good payoff. Okay, so intuitively, how would you give to the players a good payoff? You want this can happen with good probability, right? So you want P2 to be high. You want this one to be low. So this you want to make low, this you want to make high. But then also, if this recommendation happens frequently, a person who receives, for example, A1, he still needs to believe that B1 is relatively frequent. In order to play A1, player 1 needs to believe that B1 happens with high probability, rather than B2. Otherwise, he would switch to A. Okay, so we want to have this high, we want to have this low, and then also this as high as possible, not as high as possible, as high as sufficient to make players to play A1 and A2 when they hear this recommendation. Okay, so how would I do that? Well, one way to do that is, say, okay, so if we want to have this low, let's make it as low as possible.
0.
Yeah. This, we need to have some probability sufficiently high that if player 1 hears A1, he thinks that B1 happens with high probability. Okay, so say this is probability alpha, and then this by symmetry also probability alpha, and this one is 1 minus 2 alpha. Okay, so suppose we are looking at correlated equilibrium of this form, so some special sort of correlated equilibrium. So what should be the equilibrium condition?
It looks like alpha should be more than 1 minus 2 alpha.
So when I hear A1, right, it must be that I believe that this is bigger than that. Okay, so alpha must be greater than 1 minus 2 alpha. Because when they are exactly the same, these weights, we know that player 1 becomes indifferent. Now, and that would guarantee that player 1 would follow, advised to play A1. Similarly, that would guarantee that player 2 would follow, advised to play B2. Right? Now, what about other advices? For example, say player 2 hears that he should play A2. He infers from that with probability 1, the second player plays B2. And that's indeed a best reply. If I know my opponent plays B2, I will play A2. Okay, and the same for player 2. Okay, so now the only condition then for us left is this. Okay, and this tells me that alpha has to be at least 1/3. It has to be with probability at least 1/3. This has to be with probability at least 1/3. And then the remainder goes to the best cell. Okay, so now if I want to push as far as possible, I would make these things smaller. Right? I'll put all the slack probability, I will put it here. So maybe I could look at this equilibrium, 1/3, 1/3, 1/3 distribution. Okay, and then what I get is just with probability 1/3, I get 3, 0. With probability 1/3, I get 2, 2. And then with probability 1/3, I get 0, 3. Okay, and this gives me 1 and 2/3, 1 and 2/3. Okay, which is somewhere here, or 1.5. Okay, so now of course we can look for other equilibrium. But the point here is just there is sometimes a way to do better than Nash equilibrium or randomization among Nash equilibrium. So how do we achieve it? We achieve it because in a Nash equilibrium, we are forced to do independent randomization. And these bad cells, they happen with positive probabilities. In correlated equilibrium, we can get rid of bad cells, and we just use some suboptimal cells just to incentivize players. So for example, here we use the cell with probability 1/3 just to incentivize player 1 to play A1. Here we use this suboptimal cell to incentivize player 2 to play B2, right? To push them towards good cell. And in fact, in optimal correlated equilibrium, we do so in just such a way that we use the smallest probability which is sufficient to do so. We don't want to use a lot of suboptimal cells. Okay. So now let's go back. So this is just the basic construction with one example, but the general definition is, I think, is also clear, of correlated equilibrium of Alban's 1974.
And the 2 cannot be any equilibrium.
Yeah, no, it cannot be reached. Because, well, if this happens with probability 1, then
Then
it's almost
deviation.
So now, let's come back to that model of Alban. So this is 87 still, but we come back to the model by the way, so suppose in previous example, okay, so when I have this game, right? So I'm just sending you messages what to do, A1, A2, or B1, B2. And then I obtain something as a correlated equilibrium. Can I do more if I send you more sophisticated messages? For example, besides sending the recommendation, I give you an extra information about what my signal was. Can we construct more outcomes? Can we construct more distributions? So here we just mapped just expected payoffs in a correlated equilibrium. In general, correlated equilibrium is the distribution over outcomes of the game, over cells. Particularly the previous, this one was the equilibrium 1/3, 1/3, 1/3 distribution. Okay, so let's say I started with this simple construction of correlated equilibrium in which I said I just send to each of the players just the signal which equals exactly what he should play. And I obtain some outcomes like 1/3, 1/3, 1/3, maybe some other. Can I construct other outcomes in the game in this correlated fashion if I send more complicated signals? For example, I send to you a message, hey, you should play A1, and by the way, I think tomorrow is going to be raining. Or hey, you should play A1, but by the way, I think tomorrow is going to be sunny. And some extra information. Maybe this would allow me to split up my signals a little bit more and somehow devise a better outcome. Okay, so how can we think about this question?
Well, the point 2 is unobtainable, and it feels.
To do is still unobtainable.
Yes,
But-
So points close to the 2 should also be unappointed.
Yep.
So there should be some border.
Yep. Yeah, sure. So suppose, like with my previous definition of correlated equilibrium, I just obtain some thing like that. Okay, so this is what I can obtain with my definition of correlated equilibrium, which I gave you before. But now suppose I enrich the model and say, I send you each a message, but the message may contain some extra information beyond just simple strategy. So my message may be not just one symbol, it may be like a paragraph of information. Okay, so how can we model this? Okay, so suppose we have a set of messages I can send to you and a set of messages I can send to you. Okay, altogether, this gives me this whole omega set of all message pairs. Okay, so think of that as just each small omega is just an outcome of randomization which I flip at my office. And observing that, it determines which message S1 sent to the first player, which message S2 sent to the second player. Okay, let's use them M1, because they're messages, and M2. Okay, I mean particularly when I send a message to a player, I expect him to play some action. So for example, it will be some strategy, B2 for example, B1, and then maybe something else. And then here is going to be a strategy for player 1, and then maybe something else. So now, each omega then, look, what will we have here for omega? For each omega, when I receive a randomization outcome, I will know that I should send message M1, should send message M2. Okay, let's M1 be the set of all messages for player 1, and M2 set of all messages for player 2. Okay, so this M1 and M2, they partition omega for player 2, and this they also partition for player 1. Right, so we already had this construction when we talked about common knowledge. We said that we have the whole omega, and then we have information partition for player 1, and information partition for player 2. Because everything what player 1 knows here is just what message he received. Okay, and all the states which correspond to the same message to player 1, they are in the same element of the partition, player 1. Okay, so this would be the messages. But then also I say, look, when I send a message in omega, for example, I send here M2 small and M1 small. For each omega, I have this outcome function. Say it's S small of omega. It tells me outcome of the game to be played. For example, A1 and B2. Something like A1, B2, and so on. Okay, so now, so my more generalized construction would be like this. I'm thinking about all these, my possibly huge states, omega, of all my randomization devices. And a procedure in which I send you messages, M1 and M2, which just basically correspond to partition of omega into information sets of player 1 and information sets of player 2. And also for each realization of omega, the particular outcome I recommend to my players. Okay, so for this more generalized version, what should be my construction of correlated equilibrium in the more general sense? Okay, so So first of all, it should start with probability distribution P on omega. Right? So this happens with probability P of omega 1, this happens with probability P of omega 2, and so on. So say omega is finite. And now, if I have a message for player 1 that he is somewhere here, what he does is, first of all, he conditions this P on this event. Right, so say this is event E1, so he receives message M1. So he knows that he is somewhere here, he received this information. So he conditions P conditional on E1. Right, he does a Bayesian updating regarding what state he's in. So now, because how messages are organized, right? He is also advised to play a certain action, say A1. This recommendation A1 here should be optimal against what he believes the second player is recommended to do. Okay, so it's just a generalization of the previous construction. And that would be this more general version of correlated equilibrium. In which I think about a more general state of randomizations omega. So now the question is, how do this version of correlated equilibrium relates to the more simple one? So for example, when I construct such a system of recommendations and require that everybody indeed would follow the action recommended there in each state, right? I'm still interested in what's going to be the resulting distribution of over cells induced, right? So where, for example, here is going to be a cell in which they play A1, B2, here they play maybe A1, B1, and so on. So, but with some probabilities, we can combine them. So first of all, every correlated equilibrium in the first sense, in the simple sense, is also a correlated equilibrium in that more generalized sense. That's obvious. That's obvious generalization. So now suppose I have this generalized correlated equilibrium. And I'm interested in the distribution of plates in that correlated equilibrium. Is it true in general that it will correspond to the simple version of correlated equilibrium?
It seems so. I don't know.
Can you prove or disprove? Or? Well, suppose we want to prove that it is true. Let's start with a general. Say I have here some generalized correlated equilibrium. I have omega. It is partitioned for player 1. It is partitioned for player 2. And then there is this outcome function, which tells recommendations. Okay, and I know that this outcome function, the recommendations for player 1, they are measurable with respect to his partition. Recommendations for player 2, they are measurable with respect to her partitions. How could you construct a simple version of correlated equilibrium which does the same? Well, so let me just take all the information elements, information sets of player 1 when he is recommended to play action A1, for example, the same action. Okay? So in the general model, he may have one probability belief about what player 2 does here, another probability here, and the third one here. Okay, so now I say, look, this is just too fine of a model for me. I want to coarsen it. I want to make it coarse. And I say, look, in this original model, I'll send you some complicated messages. Here, let me consider the one, I still flip the coin like that, but I will only send you the message which action you should choose. Okay, so I will combine all of these green ones into one element of your information partition. You will not now be able to distinguish between these three.
How?
No, it's just originally I was telling you something more, but here I say you're just in one of these three elements. I will not give you the more information part. Okay, so I'll just make your information poor. In that sense, I'll just coarsen them, combine all of the elements of your partition, in which I recommend you the same action into one element. Okay, so that would be the coarsening of your partition. Other than that, I just keep the same prior distribution, and I just make my recommendation coarser. Okay, so my claim is that if I started with correlated equilibrium in that fine model, this would still be a correlated equilibrium in this coarser model. So for example, so suppose in the original model, conditional on this E1, it was optimal for you to play A1. Conditional on E2, it was optimal for you to play A1. And conditional on E3, it was optimal for you to play on A1. So now my claim is just conditional on E1 plus E2 plus E3, it's still optimal for you to play A1. That should be obvious. Okay, so for you it's just obvious, like this, the same constraints, they still satisfy. Okay, but now, what I do in this coarse model? Well, I just flip a coin, and I just still back to sending you a message what you play and what you play. And I obtain the same distribution outcome as I was already able to obtain the more simple version of correlated equilibrium. Okay, so what I have just proven is just, look, when we have this refined version of correlated equilibrium, it is outcome equivalent to the simple version of correlated equilibrium. And so this particular one is another way to state the Aumann's theorem in this 87 paper. In 1987 paper, he addressed the following issue. He said, look, we use in economic theory a lot the concept of equilibrium. And we say that it's maybe natural to look at Nash equilibrium or some other equilibrium. But then on the other hand, we have notion of Bayesian rationality, which is due to Savage, in which we have a decision maker who has some probability beliefs over how opponents are playing and picks the action which is best. And it is not clear how people, from just being Bayesian rational, somehow achieve a Nash equilibrium today. So in his 1987 paper, he tries to argue that, to quote, a notion of equilibrium for everyone who adheres to the Bayesian point of view is an unavoidable consequence. So it's basically like a Bayesian rational. If you believe in Bayesian rational players, then you should conclude that they play Nash equilibrium, or not Nash equilibrium, just an equilibrium in his model, correlated form. So here is how he proceeds. He says, look, okay, so how we model a game and what players do in this game, maybe the following. We imagine the state of the world omega, which corresponds to everything which could happen in the game, and maybe something else. Each state omega, in particularly, corresponds to a particular player of the game. So this outcome function. So like, if a true state omega happens, this is what will be played. If another state happens, this is what extra will be played. And then he said that, look, player 1 and player 2, they do not observe the true states of the world. Instead, they observe partitions. They observe some partial information. And now, if they have the same common prior, this is a common prior assumption. This P is the same for both of them. And if they just take this information partitioning, do Bayesian update, and in each state of the world they base rational, meaning that they select the action which is optimal given their belief, then the distribution of play, which is induced in this game, is a correlated equilibrium. Okay, so this is more like a by construction, plus that transition which I just showed you. Like how this fine correlated equilibrium corresponds to the simple one. Okay, so now, and then he proceeds to argue that this is a model is without loss and that common prior assumption is a good assumption and so on. And it's a very famous paper, but this is also a good example of a paper which is troublesome on many dimensions. Like the way he models it and argues, like shows a lot of tricky steps in argument, in philosophical arguments he does, like a lot of trickery. I think there is someone who is going to present a critique by Fargood on this paper. A comment on Aumann's Bayesian point of view, the paper is called. It's surely it's among the list of papers I assigned. And I think Gould argues quite convincingly. But there are many problems with Aumann's argument. So in particular, one of the problems is, look, so here, when we start with such a model, omega, and we say that each state of the world has already assigned actions to both players. Here is what player 1 should do, and here is what player 2 should do. So, well, first of all, player 1 here has a belief about what he should be doing in the state of the world, which may be troublesome. How can I believe about my choice if in Savage world, in Savage idea of Bayesian rationality, I have belief only about things which are extraneous to me, I cannot affect them, states of the world. And after I form these beliefs, I can choose my action. So to that, Aumann replies something like, look, this is just not a actual belief about the player, what he should do, this is just some part of the representation. Fine. Another problem is that, for example, if, say, but by the way, everything which I have said so far extends to 3 players, 4-player games, and so on. So this is not just two-player games. Another one is just, say we look at A1 here in state omega. So this A1 simultaneously is the action which player 1 is recommended to do, or what he actually chooses in the state. And also at the same time it's a action which player 2 believes player 1 will choose. And also at the same time, action which player 3 thinks that player 2 believes player 1 will choose, and so on. But all these things are different objects. So action which player 1 actually chooses, A1, and action that player 2 believes that player 1 will choose, these are different things. They're different objects. But in that model, they are assigned the same letter, A1, you see, A1 hat. So the second part of the problem with this model is that it is not formal, in the sense that it is not, it doesn't use a precise symbolism. So there is a kind of desire when we write down a good mathematical model, a good formal model, something. We need to use different letters for different objects. Otherwise, we will start a confusion. And this is what happens here, part of the problem. The third part of the problem, how he argues in favor of common prior, and this is addressed by Gould, for Gould. But here just before we, yeah, for the last 2 minutes. So here is part of his argument in favor of common prior. So he says the following. Let's take a machine planning game. So we have a game, it's actually like that. 1 minus 1, 1 minus 1, minus 1, 1, minus 1, 1. Okay, so it's a zero-sum game. So in particularly, if I ask outside observer what he thinks will happen in this game, he will tell that the case of the set of payoffs which are possible for player 1 and for player 2 is just somewhere here on this line. Now, if we allow for players who do not have common prior here, by the way, in every correlated equilibrium, the expected payoff of each player is also 0 here. You could show it in a zero-sum game. So meaning that, okay, so if we have common prior, this game still looks for each player as a zero-sum game. But now, what happens if we do not allow for common prior? Well, I'm player 1. I come and I say maybe I need to assign some probabilities. Maybe I assign probability that this happens with probability, say, 1/3. This happens with probability 2/3. If I come from savage world. So this is what my beliefs are. And then I say, look, 1/3 is here, 1/3 is there, 2/3 is there, I better play A2. Okay, so my expected payoff, expectation of U1, right? Conditional plane A2 against 1/3 B1, 2/3 B2. So this is just minus 1/3 plus 2/3 is just 1/3. Okay, so suddenly a person who is not objectively Bayesian, for example, here he believes 1/3 2/3, he expects something positive. Then maybe another person here, for example, he believes 1/3 2/3, and then for him the expected payoff will be 1/3, 1/3. Okay, and if we ask player 1 and we ask player 2 separately, they both tell us that they expect 1/3, 1/3 to obtain. Which Alman argues is a convincing argument against common priors, against not using common prior. Because under a common prior, they would all expect that it's a zero-sum game. But if we allow for arbitrary subjective beliefs, they could report that I expect to get 1/3.
But it's just expectation, it's not the actual.
Yes, I would agree with that. So Alman pushes that as an explanation that it is actually a case against common prior. But here the trick is, what's the trickery? What's the cheat? It's just when we think about this 1/3 and that 1/3, this is just in the mind of player 1, and this is in the mind of player 2. From the point of view of a single person, the game is still zero-sum. Like say, if I'm outside observer, I will expect somewhere here. If you ask player 1, he will expect somewhere here as well. Player 2, he will expect somewhere here. So Alman says that it's a case against common prior. I would say equally likely that it's just a case against looking at the outcome of the non-cooperative game from perspective of the diverse objective players. When we describe outcome of the game, what happens in the game, we need to stick to a single person perspective. We cannot switch and jump between different players when we're trying to evaluate the outcome of the game. So here what we did, we just jumped from one player to another player, and we got nonsense. If we stayed within the mind of just a single player, they would still view it as a zero-sum game. And many other things. So it's just the paper is very famous, but it's also famously problematic in that regard. Okay, so let's have a break for 10 minutes.
N1, 2 это же просто
Игроков, два человека.
и F2 вот здесь четко должен быть 1, 2, 3, 4, 5, 6.
А, да, спасибо. Ага, да, вот так самое.
Причем, а если в задаче, например, сказано, типа, докажите, что ничего не может быть, а ты там, типа, вдруг нашел контрпример, просто пишешь контрпример и все. Спасибо.
Сейчас. Вы про задачу, где эти на шахматной доске, да, вот это?
Да.
Сейчас, to make sure, что вы, я правильно понимаю одинаковые условия. Там, смотрите как.
Сейчас путь это то, что по сторонам.
И по сторонам тоже. По диагоналям.
Вот если по диагонали, то не получается. Точнее, если не по диагонали, то не получается.
Слушайте, по диагоналям тоже можно. Ну окей, да, это я протупил, короче.
В этом условии имеется.
Ну я согласен, да, я просто неправильно условия по диагоналям. Там, да, там, короче, правильно версия этой задачи, тут должна, ну то есть как бы вы хорошо, то есть то, что нашли ошибку, то как пишите код, например, зачту. Да, там по-хорошему, там правильно вот так вот и вот так вот еще можно ходить.
Да.
Вот в одну сторону.
В одну сторону, окей.
Да. Это хекс просто на самом деле.
Да. Ну, а без диагонали, да, без
Для диагонали, да. Ну, это я что-то когда писал, не заметил, что. Я просто хотел переписать так, чтобы это не было видно, что это хекс.
Ну понятно, да.
Потому что иначе там люди просто загуглят, типа там доказательства.
Задача 12 этих стоит.
Ну да. Ну, а так как я этот самый не усмотрел, что забыл про вот эту вещь. Ну а хекс вы знаете, да?
Ну да.
Там у Дэвида Гейла просто есть красивая статья про то, что доказательство того, что в хексе нет ничьей, эквивалентно теореме Брауэра.
Ну да. Там есть через теорему, то есть теорема Брауэра, она эквивалентна вот этой теореме Хекса, но сама теорема Хекса, она как-то намного проще оказывается.
На самом деле не уверен, потому что как? Это если...
Там просто, по-моему, какой-то там, ищешь просто пути из одной вершины.
Ну ты ходишь просто по кругу там как-то, да? Ну окей, хорошо, она проще...
Ну там, без теоремы Брауэра там доказательства на 2 абзаца или 3 есть. А когда ты доказываешь эквивалентность теоремы Брауэра, там что-то сложное начинается.
Там просто же, наверное, это... Потому что это двумерный случай, да, поэтому это проще.
Да, то есть там ты просто рисуешь, то есть если есть там соседние 2 шестиугольные клетки, которые разного цвета, ты между ними рисуешь черную перегородку, и потом начинаешь с какой-то вершины, то есть начинаешь из угла, тут там она и есть как перегородка, и просто начинаешь идти, то есть просто идешь, и ты в какую-то сторону, в какой-то этот.
Ну ты же, это же как бы, ты идешь, там, допустим, как-то по кругу.
И ты где-то остановишься, то есть ты все время, то есть там можно доказать, что ты будешь все время идти, пока не стукнешься в какую-нибудь сторону.
Да, ты можешь в ту же самую стукнуться, это же тебя не спасет. Там все равно в итоге вот это доказательство, оно как это лемма Шпернера примерно использует, и это примерно то же самое, что...
Я сейчас не помню.
Ну, короче, да, в общем, я с этим я налажал. Ну ладно, хорошо, что заметили. А вы про хекс где слышали? Ну там просто, как мне кажется, что вот именно такое рассуждение, которое есть, оно вроде легитимно, но оно не совсем строго. Там два абзаца. То есть именно строго, оно как бы...
Ну, наверное, есть в интернете.
Там, возможно, еще просто как бы у этого... Там многомерный еще хекс.
Да, вот многомерно там, наверное,
Сложнее.
сложнее доказательства должно быть.
Но-
Потому что там кажется, что ты просто берешь вот эту вот линию, которая разграничивает синие и красные,
Мгм.
условно. И там с одной стороны от нее синие,
Угу.
с другой стороны красные.
А, ну то есть это типа да. Угу.
И таких линий типа две,
Угу.
и они там как-то...
Ну они не могут, да. Не знаю, может быть, да. Просто как бы интуитивно, да, это понятно, но это просто как бы строго формально, если начинать записывать, то это может быть все-таки переходит как раз к тому же доказательству.
Может быть.
Это как типа, знаете, вот эта теорема Пиано, да, что это? Замкнутая кривая без пересечения делит плоскость на
Да,
два
это
кривых.
тут очень сложно.
Да, и это, то есть интуитивно это вроде как бы понятно, а
Доказательство какое-то.
то есть это может быть из такого же рода просто, что как бы на каком-то уровне интуиция, оно совсем простое, а если строго, то оно напоминает такой же теорему Пирагора. Ну, то есть теорема Брауэра же на плоскости, она же непростая, не проще, чем не сложнее, чем в трехмерном.
Теорема Брауэра, да.
Но просто из Хекса можно увидеть теорему Брауэра, например.
Да, ну вот это типа, это как-то, по-моему, посложнее, чем просто хекс заказать.
Ну, в общем, рекомендую эту статью Дэвида Гейла. Она красивая все. Дэвид Гейл там про Хекс и что-то. Хекс и Брауэр. Такая красивая.
Спасибо.
Так, сейчас я открою это. Okay, so now we do the next paper, which is to jest kamienica and Gęsko. Yeah, it's called Bayesian persuasion. Это 2011 год, 2011, because currently it's a highly influential paper that because it gave people, like theorists, kind of a direction, underexplored direction, and many people started writing follow-up papers about this one. The basic paper is quite simple. So it's about it's kind of similar in spirit to this idea of correlated equilibrium in which we want to implement something. Only in correlated equilibrium we had me, like a mechanism designer, who tries to influence players and implement. Okay, so now in this one we have just two players. Player one, who's called sender, and we have the second player who's called the receiver. And receiver learns some information about the world and tries to take action. And sender, he affects information. So, for example, there is a setting in which sender knows everything about the true state of the world and tries to communicate information to the receiver. Receiver learns information and takes action. Both sender and receiver, they're interested in action. So in the setting in which sender knows everything about the world and the receiver just learns from message of the sender, which is supposed to send. This is called chip talk game. Chip talk. Yeah. So this is from 1989, from 1980s. It's Crawford and Sobel paper, chip talk game. This is a situation in which this guy knows everything and just tries to affect action. Okay. This one is a situation in which they both do not know much, but sender chooses the way in which information will be acquired and presented to the receiver. And the receiver then take action. So it could be the following example. So the example they have in the paper, and we will get back to it. It's a situation in which this one is a prosecutor and this one is a judge. Okay, prosecutor decides how to acquire evidence. For example, he chooses people who will testify in court, or what type of investigation will be conducted. But prosecutor by law cannot hide the result of the investigation, or cannot hide evidence which is already obtained. Okay, so they obtain the same information, but he presents it to the judge, and the judge makes a decision. For example, to put a person in prison or to acquit. It could be that the sender is a medical company which invented a drug, a medical drug, and the receiver is a government agency which approves or disapproves the use of this drug. So typically what happens, the sender, in order to persuade the receiver, the medical company, they design a particular sequence of tests to which they pre-committed in the beginning, in order to persuade the government agency that the drug is safe. It could be that this guy is a salesperson, invented a new product, or say for example it's a company, they invented a new product, and they say for example a new soft drink, like a new version of Coca-Cola, and they want to persuade customers to use it. And for example, they could organize some trial of this soft drink in a supermarket. You go to a mall and there they give you some specimens of this one. Or if it's an IT company and you are the customer, then IT company can give you 1 week free trial of its product. So types like that. So I'm a sender, you receiver, and I just design the way you learn about this information. And the crux here is just this guy takes action which affects both of them, but maybe they have misaligned preferences. This guy wants one thing, that guy wants another one. And this guy affects how the information is obtained. Okay, so when we have a model like that, it's called Bayesian persuasion right now in the literature, not chip talk. A third example maybe, say it's a business school and these potential employers of people who graduate from business school. And a business school may decide a policy how it discloses the grades of its MBAs, of its students. For example, it may say that, well, we will only report who is in top 20% of the students and who is in the bottom 80% of the students. Or maybe we will report the exact rankings of the students. Or maybe we will report rankings and GPAs and so on. And then they commit to the policy. And then the firms which observe the information about a particular student, they decide to hire or not to hire the student. So things like that. Okay, so here is the example from the paper, from second page of the paper, in which we have a judge so we have prosecutor and we have a judge. Okay, and then there is a person who is being tried. Okay, so each case is just like a random draw of criminal or not criminal. Okay, so a trial. Okay, they are suing someone for an alleged crime. So originally, when a person comes into the courtroom, it's common belief between prosecutor and the judge that with probability 70% the person is innocent, with probability 30% the person is guilty. Okay, so the probability of innocent is 70%. The probability of guilty is 30%. Let me actually. Yeah. So now, the prosecutor may decide how to run a test, how to present evidence about how to run an investigation. Having heard the investigation, the judge decides whether to put the person in jail or to acquit and let the person go free. Okay, so the payoffs are as follows. Judge +1 for just decision, 0 for unjust. And prosecutor +1 for jail and 0 for the guy being acquitted. Okay, so the prosecutor wants everyone to be put in jail, regardless, innocent, not innocent. The judge just wants to free all the innocent people and to put all the criminals into jail. So they have this conflict of interest between them. So now, in the basic setting, if a prosecutor doesn't do anything, right, so what happens? With probability 70%, the judge thinks the person is innocent, and it is best to let everybody free. Doing so would give the judge 0.7, as opposed to putting into jail, which is 0.3. Okay, so it's better for the judge to let everyone free. The prosecutor then gets 0 for this. But now suppose the prosecutor can somehow run a test. which tells, for example, test, and it has two outcomes. Okay, so for example, the prosecutor can ask the neighborhood, and as a result of this investigation, there's going to be either a conclusion that it's guilty or it's innocent. Okay, so now what both prosecutor and judge know is just the probability of the result being innocent, conditional on innocent, truly innocent. It's 4/7. Probability of innocent conditional on guilty is 0. Probability of guilty conditional on innocent it's complicated. It's 3/7, and probability of guilty conditional on guilty is 100%. So what type of test is that? It's just basically, the test is just tells you for sure whether a person is guilty. For a guilty person, it's fully informative. But it is imprecise for innocent people. Innocent people, sometimes with small probabilities, they would not be able to show that they're innocent. Imagine there is some technology like that. And both of them, they know these probabilities. So what will happen then? So the judge sees a person and sees that the prosecutor runs a test. And the judge will see only guilty or will see innocent. Conditional on the message of the test, the judge will form new probability beliefs about how likely the person is innocent, how likely the person is guilty. Okay, so suppose you see that the test comes out innocent. So what do you infer?
Well, you just count the probability of innocent if innocent in marks by Bayesian formula.
Yeah. So by Bayesian formula. So unconditional it's 70% times 4/7, right? So it's 40%. But unconditional of guilty it's 30% times 0, so it's 0. So it's with conditionally on seeing innocent, you conclude that 100% the person is innocent. Because a guilty person cannot get innocent result. Cannot get tested innocent. Right? So a judge belief is just probability that innocent conditional on innocent it's just 100%. What about probability of innocent conditional on the test coming guilty. Okay, let's compute. Okay, so that's the probability that unconditional probability ex ante that innocent person gets guilty score. So innocent persons happen with 70% probability. Okay, so that's 0.7. And conditional on that, he will get with 3/7, he will get guilty. So it's times 3/7, right? So it's 30% here. And then we also defined on the ex ante probability of getting the test coming guilty, which is this thing, 0.7 times 3/7, plus the ex ante probability of guilty person, which is 30%, times the result of the test, which is 100%. So it's just 0.3 times 100. Okay, so it's 0.3, 0.3, 0.3 here, so it's just 0.5. Okay, so here, if the judge hears that the test comes innocent, he will for sure let the guy free, because he will conclude for sure the guy is innocent. When he hears the guy is guilty, the testimony is that the guy is guilty, he will think, well, it's 50-50 now, and I'm indifferent between sending the guy to jail or not to jail. Okay, and let's just, for the sake of prosecutor, think that whenever he is indifferent, the judge chooses in favor of prosecutor. So, well, otherwise, we could tweak the test a little bit to make him just a little bit more preferring. Okay, so now what happens is just originally nobody was going to jail. Now there is a probability, and what is this probability? The probability is the exact probability that the test comes guilty, which is 60%. If probability is 60%, people will go to jail after this test. And it is just judge trying to do his best. Judge understands he doesn't want to put innocent people in jail or let criminals free. Without any information, for him the best thing was just to let everyone free. And prosecutor would be unhappy. But if prosecutor divides such a machine, with this machine, the prosecutor gets happy 60% of the time. 60% of the trials will result in jail. Okay, so it shows you that maybe there is a way to devise a test for the prosecutor, which would affect the judge and make the judge take the optimal decision for the prosecutor. Okay, and the question is, okay, so there may be some way. And the question is how can we describe such tests, and what is the way to find an optimal test? Is there a way to find it? For example, in this example, can you come up with a better test? A better meaning that it gives a better value to the prosecutor.
How do you obtain again that 60% of the time?
So 60% of the time, 70% of the time a person is innocent. Mm-hmm. Then we run the test, and 3 out of 7 he gets guilty, mm-hmm. which is altogether is 30% ex ante. And then also 30% of the time the person is guilty, we run the test and he's guilty, 100%. So it's 30% and 30%.
Okay.
So now the question is, can we generalize this thing and describe somehow this optimal way of testing? Yeah, and it seems like a very tricky question. at first, and how to devise this, and how to even find the optimal way to test. It actually turns out that it's extremely simple mathematically. And that's what I think attracted also people to this model. Okay, so here is the general model, Kamenika-Genskov. They pronounce him Kamenika. He's Bosnian, so it's like in Russian it's Kamenica. In translation, it means they did somehow in Serbian. Okay, so let me screw up. Okay, so the model is the following: we have a sender and a receiver. Receiver has a compact set of actions. Compact in some Polish space, whatever. In this example, the receiver only had 2 actions, which is a compact. And there is a finite set of states of the world. So in our previous example, the state of the world was a person either innocent or guilty. And then conditional on actions, we have u of a omega is just utility of the receiver, and v of a omega is the utility of sender. In our previous example, it was 1 when they are matched, action and true state for the judge. And it was 1 they were 1 only if A is to put in jail for the sender. And in the model, they assume that utility function u and v are continuous in the action. Okay, in case there is a continuum of actions. Okay, so that's the basic setup. And now, what is a test? A test is just generates random number of messages okay. Original belief mu0 is in the interior of delta omega. So omega is a finite state space, and we have that originally both sender and receiver think that each state is possible with positive probability. So that's just an element. So now a signal. The result of the test is a signal. It's either guilty or innocent. So a signal generates a belief about the true state of the world. So in our case, there was a signal guilty, it generated some belief. There was a signal innocent, it generated some belief. Okay, so signal is a tuple P for small s for s in large S finite. So it's a finite set of messages the signal can generate. So in our previous example we had just 2 messages and it generated posterior beliefs. So now suppose we want the signal to be Bayesian, in the sense that it takes this prior distribution over states of the world and we run some tests, generates a signal, and then generates posteriors.
Sorry, what is S? S is just S is just the set of signals.
S is a set of signals, finite set of signals. Maybe something. Oh no. Не так. Not this way. Okay, so the sender chooses the signal. Signal. Finite set of messages. So distribution over S. Okay, so in the previous case, it was just conditional on innocent or conditional on guilty. What message will be generated with which probability? Okay, so when the sender selects a signal, conditional on S, conditional the belief, the posterior belief it is just mu0 of omega times probability of S given omega divided by judge will update his belief. So now the receiver maximize action, chooses action A hat of S, which is in arc maximum of expectation with respect to measure right? So he wants to maximize his utility function, expected utility function, with respect to this posterior belief. And that's gonna be some optimal action. So if this argmax has unique value, then we are fine, we just say that he takes one. Whenever argmax has multiple values, we assume that receiver always selects the one which is best for the sender. Because we want to find a subgame perfect equilibrium of this game which is optimal for the sender. Like sender, he designs, he picks a signal and he also picks an equilibrium. What subgame perfect equilibrium? Meaning that the sender chooses this action, chooses some signal. And then, knowing the signal and the realization of the signal, the receiver makes the action which is optimal. Okay? So now we can define V hat. So this is the action conditional on signal. In general, we can define a hat which is a function of mu, right? Because instead of mu conditional on S, we can also condition on belief. Also, we can define, therefore, V hat, which is also conditional on mu, which is just expectation with respect to mu of V of a hat of mu omega. Right? This is what the sender gets if it happens that the belief is mu. Okay, so this is the definition of V hat, this is the definition of A hat. So now, what happens if we have some signal in play? So suppose I have a signal, it has S large possible realizations. So conditional on each S, it will give me a posterior belief. Right? Now, the question is, for a small s, with which probability will I see the signal S? So I run the test, right? And the test is like that. And I will see one of S large messages. So suppose I take a small, say, S tilde in large S. What is the probability of this signal?
Sum of these probabilities divided by.
I don't think it's divided. No, it's not divided. It's just P of S given omega times mu 0 of omega. Yeah, this is the probability. I'll see the signal. Okay, so that means that effectively what happens is just when I run a test, it generates me a probability distribution over posterior distributions. Okay, so this is a little bit like, so signal generates me a finite support probability distribution. Okay, so it's a finite support probability distribution over posteriors, which are themselves distributions. And this is the only thing I need to know in order to compute what is the payoff for the sender from choosing a signal, right? Because each particular posterior distribution, we know which action will be chosen and what it result to for the sender, right? Because the sender only cares about if I know this element, which is induced by the signal, this tells me how good or bad the signal is for the sender. Is it clear? Oh, what? So here is what happens, once again. So we have a signal. So now the signal generates some possible messages. Conditional on a message, we get a well-defined posterior distribution, which is in delta omega, right? This delta omega. So now, for each posterior, we know what the receiver would do and what it translates to for the sender. So now, also when I have a signal, right, I know that one posterior happens with probability P1, another happens with probability P2, and so on. So I can compute the expected value of V, which will be induced by the signal in this two-step procedure. So to compute this expected value of V, what is the sufficient information? What's the sufficient statistic for me? It's just this element. So I just need to know which posteriors and which probabilities. Right? So that's an element of this one. So now that means, okay, so I can think about very complicated signals and so on, blah, blah, blah. But eventually I'm just interested in these elements. Finite support distributions on posterior beliefs. So, so here is a question. So I start with mu0, the prior distribution over omega. And now I could devise some kind of a test from a large set. And I could obtain this element here, induced distribution over posteriors. Is there any restriction on which elements I could obtain? So for example, say I know with probability like 10% I will get, with 10% I will get mu S1, with probability 20% I get mu conditional on S2, and with probability 70%, I'll get mu conditional on S3. And I was told that the prior distribution is mu 0. Is there any correspondence? It has to be, right? Because what is this correspondence? Can you write down an equation which must be satisfied? If I indeed obtain this from a test.
Here is the prior distribution.
Yes.
The other one is the posterior given one of the signals.
So with probability 10%, I will obtain this posterior. With probability 20%, I get this posterior. Probability 30%, and this is distributions. Well, we have the formula of complete probability, right? It has to be that if I add this up, it has to equal to this. So that's one requirement. So when designing a test, okay, so I'm as if I'm choosing these posteriors and assign to them probabilities. But my restriction that I always need to choose posteriors in such a way that they sum up to the prior. Okay, so that's for sure must be satisfied. If I obtain this from a test, from a signal. But now it's a simple fact to verify that this is the only condition we need to satisfy. If I give you some posteriors like that, I could design a test which will give me this distribution. That should be also relatively straightforward. Why? It's just because, look, yes, so suppose I have, so I'll do it for these three distributions, right? So I have 10% mu conditional on S1 plus 20% conditional on S2. So it's basically for all omega, I have the following: omega conditional, and 70% of mu omega conditional on S3 equals to mu 0 of omega. Okay, and for each omega, this is positive. It's the first step in the construction. So now I know that for each omega, this is true. I want to design a test. Well, to design a test, I just need to specify conditional on omega, what's the probability of me seeing S1, seeing S2, and seeing S3, right? But this is just simple, right? This is, I get omega with probability this much, and I see S1 with probability so it's basically P of S1 conditional on omega becomes the ex-ante probability of me seeing omega and S1 together. This is 10% times mu of omega conditional on S1, which we must divide by mu 0 of omega, right? And this is going to be a correct distribution if we sum over S1 because of this equality. Just for all S large, I get this. F S2, I could assign 20% times mu of omega conditional on S2 divided by mu 0 of omega, and P of S3 conditional on omega, I could assign 70% mu of omega conditional on S3 mu 0. Because of this equality of the star, these conditional probabilities indeed sum up to 1. Therefore, it's correctly defined probability distribution of the given signal, and it would result into this element exactly. So that's basically the key idea in the whole process. Picking among signals for the sender in this game is equivalent to picking among these elements which satisfy this Bayesian equality. But now, okay, this is the first observation. Very simple. Okay, so now we're picking between the things. Now recall our definition, which was V hat of omega, V hat of mu. If I have a posterior mu or any belief mu, this is conditional on this mu. The receiver makes something, and this is the expected payoff, right? So now I have, for example, here is just omega 1, omega 2, omega 3. And then here I have mu 0, which is element of that simplex. Now, for each mu here, I can plot V hat. Right? No, it's just, okay, so let's do it. There's going to be some function. Now this is V hat of mu, the graph of it. Now, if I just do nothing, when I see mu 0, right, in the case of judge and prosecutor, if we tell nothing to the judge, he will get V hat of mu 0. But now prosecutor or the sender, he can choose among such things. But what are these things? What is this? This is just we are picking probability distributions here such that their convex hull is exactly mu 0. Right? We can convexify. So now, okay, so for example, say I pick a signal like that, and it has like, okay, so I had there, with probability, it was like S1, it just results in mu conditional on S1, mu conditional on S2, and mu conditional on S3. Okay, and we had this happens with probability 10%, 10%, 10%, 20%, and 70%. So what's the value for the sender from playing this distribution instead of mu0. So in that case, he'll get this one. In that case, he'll get that. In that case, he'll get that instead of this one. So now we get altogether these values. They're going to be summed up with the same weights.
The same weights.
With same weights 10%, 20%, and 30%, but on this vertical axis now. So what happened, and he can realize it. So instead of just picking mu0 and v of mu0, the sender can pick any 3 points on the graph of v hat and obtain everything which is between the convex hull. So it's basically, instead of function v hat, we can consider the function v. V of mu, the graph of v of mu is the convex hull Okay, so it's just basically, instead of, so I start with v hat, which I can compute from the primitives of my game easily. And now I'm interested in all this, like, this function is called concavification of v hat. We have mu, so concavification of function v hat. I can give you mathematical result. This would be I think they defined it like that. That v hat of mu equals to this from what we use letter z supremo z such that mu and z belongs to convex hull of graph of v hat. Maybe for 3 dimensions it's a little bit tricky. Let me do with 2 dimensions. and our previous example of prosecutor and the judge. Okay, so now we have, there are only two states of the world. V0 is guilty, and V1 is innocent. So now we know that the original belief is that with probability 70% the person is innocent. Okay, so this is mu0 somewhere here. So now we need to compute v hat of mu for all mu between 0 and 1. What's the hat of mu? This is how much the receiver would get if the judge believes the probability with probability mu the person is innocent. So now if the judge believes that the probability that the person is innocent is more than 50%, the person will never go to jail, and the sender will get 0. Right? So this is v hat of mu here for 50%, 0.5. If the belief is below 0.5, the judge believes the person will get is pretty bad, the person will go to jail, and the condition on that, the prosecutor will get 1. So this is another part of v hat. Okay, and now I'm interested not in these green things. I'm interested in all these convex combinations of points I can do with them. Right? And I'm interested in the upper envelope of this convex hull. So where is that? This is just this thing. So I go like that, and I go like that. So this will be V. Yeah. So now I'm back to my example. So I start with mu0. And here if I do nothing, I obtain 0. But now it tells me that I could obtain more. I could obtain this one. Okay, so how do I obtain this one? Well, I need to take a convex combination. I need to combine this posterior. This is mu1, and I need to combine this posterior, which gives me 50-50. So one posterior should give me 50-50. Another posterior should give me that with probability 1 the person is innocent. And the exact mixture is precisely like that is 60% here and 40% there, if you combine, you can compute. But this is precisely the test which we started from. Okay?
So it was 50-50?
The posterior was 50-50. The test was such that if a person is found innocent, the person is for sure innocent. If the person is found guilty, the person is innocent or guilty 50-50. And the person unconditionally, example, was found guilty with probability 60%. But this kind of like development gives you an easy way to construct this test. Like, because when I started from the example, it looked like a trickery. Like, I proposed some test and it was not, we were not sure if it was the best one and so on. But this one kind of graphical, it tells you that this is indeed the best. Why? Because, well, it just, eventually when we do a test, we just represent this original belief as a convex combination of some points. And what we get for that is just the convex combination of the values. And the best way to do that is just for sure we cannot get more than the red line. And this test which I provided precisely give you that upper bound. With 3 or more states of the world, it becomes more tricky, but the basic mathematics is the same. We find the concavity. So, in general, basically the mathematics of this is very simple. We just compute this v hat of n, and then we find this concave physical. Yeah, the function should be concave. It's like the smallest. I'm just this function v is basically, I think I might say, it's. I think I'll be correct to say it's just the smallest concave function which majorates v hat. I'm not sure why they didn't put it in these terms in the paper, but it's just the smallest concave function which is above. And when you have this function, well, you plot, you see the graph, and you know, okay, so it should be representable by convex combination with some extreme limits. And this is how you find what could be the best test. So now, in applications, of course, we start with some very abstract notion of a test, and it's not clear whether the sender will have such test readily available. Right? So when people try to do some application of this technique, right, they hopefully compute what's the optimal test, and then this optimal test actually has some simple natural form which can be implemented in real life. So that's just a thing. So today we covered Aumann correlated equilibrium, then we covered Bayesian persuasion. Tomorrow is going to be, I think, one presentation, and then also we'll start doing type structure models of epistemic game theory. And we will do it for tomorrow and next week. Yeah, by the way, we will have classes next week as well. So we'll have next week and then the final.
Вопрос. Скажите, у нас было понятие common knowledge в модели Аумана. Это там пересечение всех вот этих вот. У нас же понятие common knowledge, оно в каком-то стейте.
Да.
То есть для какого, то есть в каком-то стейте мы считаем, что вот в этом стейте вот это событие common knowledge или нет?
Да.
Просто тогда в 24 задаче там, по-моему, стейта нет. То есть там в последней просят посчитать, это же common knowledge от B, правильно?
Common knowledge от B. B это
бета-событие,
Мгм.
а state в каком?
Нет, ну подождите. Knowledge of B это оператор. Не, все.
Или просто оператор применяем,
Да,
без,
да, да,
без
да.
состояния стейта. Просто
Ну,
оператор.
у нас просто, как бы, если у нас есть этот самый какой-то event, и вот у нас есть эти partition, которые как это finance common coursing,
Да.
их вот этих partitions. И мы просто берем вот эти кирпичики, которые целиком там лежат, и вот их объединение, это будет новое.
То есть без этого.
Ага.
Хорошо, понятно. Спасибо большое. До свидания.
Professor, can I ask you also about our notion about iterative admissibility that also in the book you recommended?
So for iterative admissibility, you could look at it in lecture notes.
Okay.
Yeah, because usually in textbooks, they do not use it all that much, iterative admissibilities, underrepresented in textbooks.
Okay. In the one of perfect equilibria, you sent me a book. I remember, like in the for email, and the book you say it's in the webpage, or you send it to us.
Myerson, he has perfect to tremendous and perfect. Myerson, like that. Yes. I will send just one more time to the class.
Okay.
I think textbooks to prepare,
Okay.
because I also need to write down tickets for the exam, and I will try to write against every question where is the best place to look at.
Okay.
Myerson. Then also I think I will send you Osborne. Let me actually, while we are here. Myerson. So he goes with sequential and then refinements. So he has perfect equilibrium, chapter 5.2. Perfect and proper and existence of perfect and sequential equilibrium. You can look it up here. And also in Selkins original paper.
One from the 70s, right?
Yeah, 75. It's actually like reasonably well written. The first few pages, it's a good exposition of Kuhn's theorem on perfect recall and things like that. I would say, like, for example, this guy here, right, Myerson textbook, he has the proof of Kuhn's theorem.
What was
That's just that mixture of normal strategies.
in the
normal form, yes, is equivalent to behavioral mixtures. If a game has perfect recall. For games with perfect recall, final games with perfect recall, it doesn't matter how you model mixtures, behavioral or normal form.
Behavioral mean like it's
Behavioral meaning that in each information set I mix my actions. Okay, I mix here, I mix there, so it's more simple object. A normal form means I like, it's basically like, do I flip a coin once before the game starts and then play pure strategy? Or do I flip a coin at every information set? And it doesn't matter for such games. For yes, so it's a bit kind of like clumsy here. It's not difficult. It's clumsy, and I think Kuhn he has a cleaner exposition. Or not Kuhn, Selden, yes, at the beginning of his paper. There's a cleaner exposition than even in the textbook. Yeah, but basically chapter 5 of Meyerson. So Meyerson for sure I sent it. I could send it to you right now, just to be sure.
And there's also some examples there to.
Mm-hmm. There was an example of sequential equilibrium recovered from that book.
About the value of a game, maybe?
Probably, yes. I'll send you.
Because like so you see like in the value, so say player 2 first maximizes and then player 1 minimizes his loss, right? So of the definition. And so we're interested in the case where we allow mixtures. The strategy is
Yes.
here. And for instance, in the case where we studied today in the beginning of the class, remember that player 2 will only mix if player 1 has beta equals 1/2 or something like that. So we would have to analyze like for intervals, like if beta is 0 and less than 1/2, then player 2 will always have one strategy. And then with 1/2, you will have mixing with something, and the other part you will have also pure strategy. So it will be 3 instances in which we have to take a look to find the value of the game.
No. Value of the game is value of the game is a value in Nash equilibrium. In the equilibrium of the game.
Oh, set the value in a mixed strategy.
So when you have a zero-sum game, there could be multiple Nash equilibrium mixed strategies. In all of these Nash equilibria, player 1 gets the same payoff.
Okay.
And this is the value of the game.
Oh, okay. It may be like how. Okay. Countably, maybe. No, I guess in this case we have only one mixed strategy here, and in zero sum you say we can have multiple like.
We could have continuum of them because if
can we have like finite, not different from one? Can we have like 2 or 3 or is it?
no, no. It's always infinite. Because why? Because if I have one Nash equilibrium in which I play say mixed strategy sigma 1, another one I play mixed strategy sigma 2 in zero sum games. Any mixture between sigma 1 and sigma 2 is also equilibrium strategy.
So okay.
Yeah, because it's maximum strategy. And I got min-max strategy. It's just basically like as long as I play my maximum strategy, it's a part of Nash equilibrium. Like if I take any maximum strategy for me and you take any maximum strategy for you, we combine them and it's a Nash equilibrium.
I see.
So it's for sure it has to be like a continuum, like it's a comics. But in all of them, I get the same payoff. Yeah. And this is a value of the game.
Okay, that's good value.
Okay. Yeah, it should be in lecture notes which is sent, and then okay, so Osborne Rubinstein, one textbook, and then also Meyerson. Meyerson. Yeah. Okay. I'll send eventually. I'll send to everyone else textbooks as well when I write down the question related.
Okay.
Thank you very much.
преимуществ. Именно только критерий дорогости.
Слушай, у меня дорожный цикл это самого цикла как бы без каких-то дополнительных без дополнительной информации непонятно. Нужно хотя бы знать, как устроены там его остальные ситуации. То есть, видишь, немонодробность, она возникает из-за того, что есть температура. И то, что они есть, но всегда односторонне так не надо. Фазовый портрет нового карты. Ну, то есть, собственно, всего потенциала. Если хочется узнать, если является ли он частью более большого надзора, то это вообще очень глобально. Продолжать всю историю глобальности. Я знаю, пересадить карточку, кстати, если убегаешь, у тебя платно. Выбирай сам. А может быть, не стоит, может стоит. Прошлый раз. Первый раз. Скорее всего, они как-то системы связаны. Иначе я же опять
Еще не раз. Один. Серьезно?